Our next speaker is Rebecka Jacobsson. She's a machine learning lead at iZettle, a member of the PayPal family, on a mission to help small businesses succeed in a world of giants. Rebecka is also one of the founders of Women of Data Science in Sweden, a network for current and aspiring female data scientists that arranges technical conferences and events. She will talk about feature engineering and feature stores at iZettle. Welcome, Rebecka. She's also here in person, so she's just entering the stage as we speak.
Thank you for inviting me to be here. This is really fun to get a chance to talk about a topic that I care about. So I'm Rebecka Jacobsson. I head up the machine learning team at iZettle, and I'm here to talk about how we have designed a core part of our machine learning infrastructure, which we call our feature library. And I'm not here to kind of say this is how to design a feature library in general, or this is like the way to do it at your company. But I'm here to sort of show off what we have done as an example, and I'm hoping that can serve as inspiration for those of you who might be facing similar challenges at other places. So I'm going to start by talking a little bit about machine learning at iZettle, both the company and the team, kind of what we do and what types of problems we work on. And that will help kind of explain what needs we have when it comes to feature building and what the requirements were when we set out to build this feature library. I'll talk briefly about what solutions already exist on the market to this problem, because there are some out there, but we ended up building our own. So I'll also talk about how we built our own, sort of how we started and then how we've iterated from there. And finally, I'll end with some key takeaways. So, iZettle. Some of you might have heard of iZettle already. We're a Swedish fintech company founded in 2011. We were acquired by PayPal, a big American fintech, in 2018. And we're most known for our card reader, which is on this slide. So this is our most famous product. If you live in EU or Latin America, you might have used it to pay for a takeout coffee or a haircut. What we do in general is not just card readers or card payments. We build tools and services for small businesses. So that's kind of our niche. We build tools that are specifically adapted to the needs of small businesses as opposed to larger businesses. I've listed some of our other products here. I'm not going to talk about all of them. I'll just briefly mention, for example, one of our products that we have in addition to the card reader is lending. So it's possible to get a loan via iZettle if you are using our card reader to process transactions. So you might wonder what we use machine learning for, and that's not an obvious answer. So we haven't always had a machine learning team at iZettle. The team was formed in 2017. When I joined iZettle in 2016, there was no machine learning team, and I joined the credit team. So I was working purely on building credit scoring models for our lending product. And there was one other machine learning use case at iZettle at that time, which was fraud detection. So using machine learning to kind of find the bad guys using our platform. In 2017, the team was formed, and since then we've grown a lot. So we started with 4 people, and at this point we're 8, so we've doubled in size in 3 years. We've also added a bunch of other areas that we cover. So today we also work with predicting lifetime value and use that for optimizing our online marketing. We have worked a lot with our sales department on sort of optimizing how we work there, and we've been involved in various retention efforts, so predicting churn, for example. Now I'd like to talk a bit more in detail about the ML problems that we work on and kind of some of the characteristics that they share. So first of all, and maybe most importantly, what most of them have in common is that we aim to predict something about the future. And I've made the predict bold on my slide because I think as ML engineers or data scientists, we tend to sometimes use these phrases interchangeably. We talk about prediction and classification as if they're the same thing. And I have the firm belief that they're not. I could give an entire talk about why. But I think we sometimes confuse ourselves when we use them interchangeably because they have very different sets of challenges. And one challenge when what you're trying to do is predict the future is you need to be super careful about how you construct your features so that you don't accidentally leak data from the future back into the past when you're training your model. Another thing that characterizes our machine learning problems is that they usually all apply to the same kind of entity. In our case, that's a small business, or we call it an organization. So what this means is regardless of whether we're trying to predict churn, offer a loan, or determine whether an organization is fraudulent, what we're trying to do is make one prediction per organization. And this is actually like very nice because it means our problems have a lot in common with each other, and so we can kind of reuse a lot of our thinking. Another thing that many of our problems have in common is that they use overlapping feature sets. So an example of a feature that we commonly use would be the number of transactions that have been processed in the past 10 days. That's something you can imagine is useful regardless of whether you're trying to estimate someone's creditworthiness or you're trying to say if this merchant is fraudulent or if we're trying to guess if they're going to churn in the next month. Finally, one characteristic of our ML problems is that they typically run predictions in batch mode. So we currently don't have any real-time ML applications. That will probably change in the future, but for now it's actually very nice because it allows us to keep our data infrastructure and ML infrastructure a lot simpler. So our machine learning projects, they vary a lot in sort of size and complexity. What they do typically have in common is that a machine learning project has a limited lifetime. So when we build a model, we don't expect it to live forever or for 10 years. We know when we start that it's not going to live forever, and we will need to retrain, and once in a while we'll kind of go back and even rephrase the problem. The image here on the slide on the left tries to give like a schematic overview of our machine learning pipeline. I've chosen to focus here on our machine learning pipeline rather than our entire data infrastructure because that's a huge topic. So this is the way that we've come to think about most of our machine learning problems as consisting of these three separate parts: the universe, features, and then training or prediction, depending on what kind of pipeline this is. So what we do is we run scripts in Docker containers, we use Python, and then we schedule those containers to run using Airflow. And the first part in the pipeline is what we call a universe. I know this is not like a well-established phrase, but I'm trying to establish it here now. So what we mean by universe is something that answers who are we making predictions for. So it kind of defines the problem space. So typically a universe, let's say we're doing credit scoring, it will consist of a list of organization UIDs. If we're training a credit scoring model, it will be a list of organizations that we have issued loans to in the past. So they are the ones that we want to learn from. It also includes something we call a data horizon, and this is basically the point in time at which we would like to make predictions or learn from. So in the loan example, it'll be the time that we did issue the loan. And then the label is what it sounds like. If we're talking loans, it's did they pay back the loan in the end or not. A prediction universe will look almost the same. It won't have a label column because that's obviously what we're trying to predict. But it'll have a list of organizations that we want to make a decision for. Do we want to offer these organizations a loan or not? And it'll have a data horizon column, which is the point in time at which we want to make the prediction. So typically today, if we're running the pipeline today. The next step in the pipeline is feature creation. So this is what I'll talk mostly about today, but for now I'll just say that this comes after the universe creation. And the universe is basically the input to the feature step. So because we make predictions, because we care about this data horizon concept, we kind of need to define the universe first to be able to say when to build features for. So the universe, the organization, and the data horizon are all like important inputs for building the features. So if we're building a feature like the number of transactions in the past 10 days, we need to know at which point in time do we want to count those 10 days. So if we're training on loans that we issued in the past, we want to go back to the date of issuance and look at the 10 days up until that point. And this is important to get right. The output of the universe is essentially a table consisting of the three first columns in this example table on the slide. And we send that into the feature step. And after the feature step, we've essentially added more columns to it. So in practice, all we're doing is building this table, which can be stored anywhere. In our case, we store it on BigQuery. The final step of the pipeline looks different depending on whether we're training or predicting. But in training, we do exactly what it sounds like. We train a model, and we typically store a pickled model object somewhere for later usage. If we're predicting, what we'll do is we'll take the universe and the features, and we'll feed that into our trained model, and we'll get some probabilities as output. So I promised I would dig into features. And the reason that we have dug into features is that this is something we recognized fairly early as something we'd like to address. So we concluded early that there will be a lot of overlap between the feature sets used by our models, and we don't want to reinvent the wheel every time we build a new model. So we basically concluded that we would like to be able to reuse features across multiple models and not have to re-implement a feature like number of transactions in the last 10 days over and over again. There were also some other sort of constraints or criteria when we started thinking about our feature building needs. One of them is point-in-time correctness, which I've already talked about. It's kind of the importance of calculating the feature at the correct point in time and not sort of leaking data from today into the past. And finally, an important aspect, which has gotten a lot of attention recently, is consistency across training and prediction tasks. So if you end up building two separate feature building pipelines, one for training and one for prediction, there's a risk that they won't match. And if they don't match, you might have very inaccurate predictions, and it's something we want to avoid. So in our case, the goal was to be able to use the same code when creating features for training and when building features at prediction time. There's also a few things that are not so important for us. One of them is computational efficiency. And the point here is not that we don't care at all about our algorithms or processing being efficient, but it's not a priority. And that's for a few reasons. One of them is that our data sets aren't huge. This obviously depends on who you would compare to, but it's usually not a limiting factor to us. Another reason is that we are completely cloud-based. All of our data processing happens on Google Cloud, which means that we can basically scale indefinitely. So we usually can sort of make a job finish in whatever time frame we need by just throwing more resources at it. This obviously doesn't mean that we are sort of willing to put up with anything, but it means that our tolerance for inefficient jobs is relatively high because we can kind of live with not having an optimal performance as long as that has like a benefit of, for example, keeping our code base simpler. Another aspect that's not so important for us is storage and serving. And this comes back to the fact that we mostly run predictions in batch mode. So we don't have this challenge that I know many others have of serving feature values in real time. You might wonder, isn't this already a solved problem? Haven't others done this already? And the answer is yes, but not in 2017. So when we started doing this, we did go out and kind of look for solutions to this problem. We expected to find something. We expected to find some open source framework for how to deal with these things, but we didn't. What we were able to find was blog posts and some conference talks from companies like Uber and Airbnb, who had basically built their own solutions to this problem. And that was really inspiring, but not directly useful for us because we couldn't use their code because they hadn't open sourced it. Since then, a lot has happened in this field. There are tons and tons of sort of feature stores and feature libraries out there. I think that's really exciting. Some of them are super interesting and good. We aren't using any of them, and it's partially because we had kind of already started building our own, but also because they don't always match kind of the problems that we have. So many of them are focused specifically on feature storage and serving, which is sort of a very valid, important use case, but not for us. And they're also often limited to a specific cloud provider or a specific data processing framework for building the features like Spark. And so if this doesn't match what we're after, it's not a great fit. But in the future, we might definitely use some of these. But what we ended up doing was instead building our own. And when I say we built our own, I sometimes think this sounds like, we sat down for 6 months and we planned very carefully exactly what we'd build, and then we put a team of 10 engineers on the problem. That's extremely far from the truth. And so what I want to convey here is that we started embarrassingly simple. And I'm showing you some literally embarrassing screenshots of old PRs that I made to illustrate my point. The very first thing we did was basically refactor an existing model. So taking the feature building code and breaking it out of the other code for that model, and that was it. So super simple, fairly dumb. You can see that my first attempt of making a PR here was even closed. But basically at this point, our feature building code was pandas and SQL code glued together. It was only being used by one model. The only way to run it was to kind of run the entire script, and you would get all the available features back. And it was terrible. It had really bad performance. There were a lot of bugs in there. Yeah, it wasn't great in any way. But this is how we started. Luckily, we didn't stop there. So after that, we iterated. We started to have more people using this logic. We started using it across more different models at iZettle. And that really helped because it meant we discovered bugs and we could fix them. It also meant we had a lot more smart people working on the problem and coming up with good ideas for new features and how we could kind of expand on this framework and make it serve our needs better. So over time, we added some flexibility so that you can now sort of build the features that you want and not just get everything all at once. After a while, we added some parallel processing capabilities, so we moved away from the pure sort of SQL and pandas, and nowadays we use Beam for calculating some of our features, or the sort of heavy ones. But most importantly, we refactored and refactored and refactored again. And I think this was an important learning, that it was impossible to predict our needs and what we would need in the future. So we had to kind of do it as we were going along. So today, our feature library is a containerized application. It's used by all of our machine learning models in production. And the structure that we've settled for is what I've tried to sort of illustrate schematically on this slide, which is where we try to separate sources, which are essentially queries that extract raw data from some data source. We've separated that from the actual processing logic, which we call feature groups. And it's basically a way of structuring our code to make it cleaner and possible to kind of puzzle together different pieces. We've also separated these two, which are kind of the definitions of the features, from the code that actually runs it. So the extractors and runners, that's kind of glue code concerned with like piecing all of this together. And I'm sharing this not because I think it's the right solution. I think there is no right solution, but just to show sort of where we've ended up after a few years of iterating on this problem. We consider our feature library to be a core part of our machine learning infrastructure, but we're not done. It's under constant development. And so what I'm showing here is not like a final state in any sense. To wrap up, I think the conclusion is that at iZettle, investing in this shared feature building library has helped us to develop new models a lot faster than we would have without it. It has helped us collaborate more because we have this shared piece of infrastructure to collaborate around. And it has helped us produce a lot more accurate models, basically because we have more eyes on every problem and piece of code. I think some of the important success factors were to start small and iterate, as I've said several times already, and also that we managed to have sort of many people using this pretty early, so we could pool like brain power from multiple people. Finally, if any of this sounds like fun, we're hiring at iZettle. Otherwise, I think that's kind of what I had to cover. Thank you for listening.
Thank you, Rebecka. Very interesting. So we have 3 minutes before the next speaker. So I will just pick a few of them here. We have one from Elin. So when do you think it's worth to do batch inference versus continuous streaming inference? You mentioned that you're only doing batch right
I think depends completely on your use case.
Okay, so
you can get away with batch predictions. I would totally go for that any day of the week because it's so much easier.
Okay, but don't you you haven't seen any like major performance improvements in doing real-time feature?
No, but again, it depends on our use cases. So for the loans, for example, we only need to make decisions once per day. There's no need to kind of make a decision depending on sort of real-time user input. If we had that need, obviously, we'd sort of have to build our infrastructure a bit differently to address it.
You have no fraud use cases, for example?
We do, but we're able to handle that in batch mode as well, actually.
Okay, cool.
So basically, what we do is transactions happen all throughout the day, and then we can run like our ML models for risk detection during the night. And we have basically what we do is we use machine learning to suggest cases that seem suspicious to our risk analysts, and then they review them in the morning before we pay out the money to the bank account of the merchant using iZettle. So it's possible to do even that in batch mode for us.
Great. So we have another question from Rasmus. Could you maybe exemplify a bit what you mean by leaking information from the predictions into the training data?
Yes, I didn't mean so much leaking from the prediction, but so let's take the example I was using throughout. So if we're looking at number of transactions in the past 10 days, if I have a loan that was issued 3 years ago and it defaulted, so it failed to pay back 2 years ago, if I look at the number of transactions in the past 10 days now, when I'm training, that might be 0 because they defaulted on their loan. We might have kicked them out of iZettle or they're bankrupt. So I could use that, but if I do, that's not information that I actually had access to when I was making the prediction, when we were issuing the loan. So I'll be kind of, leaking information from the future if I say, it's really low or it's 0. What I should be looking at is the information that I did have available at the time when we were making the decision on issuing the loan or not. So I don't know if that helped, but that's what I mean. By leaking information.
One of the main issues with building a feature library.
Yes, for sure.
Okay, thank you, Rebecka. Very nice.
Thank you.
And here comes Anna with some flowers.
Thank you very much.
Thank you.